You know, we all think we have a pretty good handle on probability. It's just the chance of something happening, right? But what if I told you that the entire mathematical framework we use for it is missing something? Something huge. An ingredient it actually used to have, but is somehow forgotten along the way.
So yeah, that's the big question for today. What if probability itself has amnesia? A fascinating new paper suggests our entire understanding of it is like a person who knows exactly where they are right now, but has absolutely no memory of how they got there. And you know what? Recovering that memory could change, well, pretty much everything.
And this is not just some fancy metaphor. The source material gives this condition a name: epistemic presentism. It's described as a kind of systemic flaw in our thinking, where the entire history of how we formed a belief, all the data, all the wrong turns, all the evidence we gathered, it just gets erased from the final picture.
To really get this, we've got to go way back, all the way back to Plato's cave. The core idea here is that for centuries, we've basically been prisoners, staring at shadows flickering on a cave wall and thinking that's reality. We've built these incredibly complex theories about the shadows, but we forgot to ask the most important question of all.
This quote just nails it, doesn't it? Our current probability theory, that's the shadow play. We are absolute experts at describing the shadows, but we completely forgot about the real, solid objects that are casting them in the first place. So, what's keeping us chained up in this cave?
Well, those chains actually have a name: normalization. It's a single, totally innocent-looking step in our math that has these huge, profound consequences. This one little operation is what's giving probability its amnesia. Let's break down how it works.
So here's the deal. You start with all your evidence, which has two components: its shape, kind of like its distribution, and its total weight or mass. Normalization takes that total weight, uses it just once to make sure all the probabilities add up to 1, and then it throws it away. It literally discards the entire history of evidence you collected. The paper calls this ontological surgery, which is just a perfect phrase. Okay, so step 1. You start with your raw evidence, right? It has both a shape and a total weight. Step 2. You sum up that entire evidential journey into a single number. And then, step 3, this is the cut. You discard that total. You throw away the very thing that gives your belief its weight, its history, its substance. And what are you left with? Step 4, just the shadow. A clean, normalized shape with no memory of how it came to be.
So if our entire concept of probability is just a memoryless shadow, then what in the world is the real object casting it? Well, to find out, we have to break the chains, we have to turn around, and we have to finally step outside the cave.
And what we find outside the cave is that reality isn't this flat, two-dimensional world on a wall. Oh no, it's a much richer, higher-dimensional space. The shadows we've been obsessing over are just one projection, one slice of a much more interesting and complex reality.
Let's put it side by side. Inside the cave, all we can see is the shadow. That's probability, P. It only has a shape. But outside, in the real world, we see the full substance. It's that same shape, but it's combined with its total evidential mass, M. For centuries, we've been operating without that M, without the memory.
So this missing dimension, let's give it a name. We'll call it rho. And rho isn't just some abstract number. It represents the total amount of evidence you've gathered. It's the literal thermodynamic work your brain had to do to learn something. It is the path you took to arrive at your belief. It's the history that normalization just threw in the trash.
Okay, so why does any of this matter in the real world? It matters because when we recover this lost dimension, it reveals a pretty profound truth. How you get to a conclusion is just as important as the conclusion itself. Your journey, the path you take through the landscape of ideas, has a shape. And it turns out that shape determines how justified your belief really is.
Think about it like this. Imagine two scientists. They both end up at the exact same correct conclusion. But the first scientist got there through a direct, logical, efficient path. The second one, well, they kind of stumbled upon it after a whole series of wrong turns, dead ends, and lucky guesses. Now, standard probability says their beliefs are identical. But ask yourself, who would you trust more?
The efficient scientist, her path is like a straight line. She accumulates evidence cleanly, directly. And in the language of this new geometry, her path has very low curvature. The result? A belief that's highly trusted and very strongly justified. But the wandering scientist? His path is all twisted and inefficient. He wasted so much effort on bad hypotheses, he had to backtrack constantly. His journey has very high curvature. And even though he got the right answer in the end, his path tells a story of unreliability. The result is low trust and really weak justification.
And this brings us to this really cool and crucial idea of curvature. You can think of it as the geometric scar tissue that gets left behind by a messy, inefficient journey. It's a measure of just how twisted your path to knowledge was. A straight, direct path leaves no scars. A crooked path is covered in them.
Now, I know this might sound a little bit abstract, but stick with me, because this new geometric way of looking at things has incredible power. It can actually solve philosophical puzzles that have had people stumped for decades.
So, let's take the famous problem of old evidence. Here's the puzzle. When Einstein was developing general relativity, the weird orbit of the planet Mercury was already a known fact. Standard probability theory says if you already know something is 100% true, it can't offer any new confirmation for a theory. It's old news. And yet, everyone agreed that explaining Mercury's orbit was this massive, stunning success for Einstein. So, how is that even possible?
This new idea gives us the answer. See, the evidence itself, Mercury's orbit, that didn't change. What changed was the path to that evidence. For the old Newtonian physics, Mercury's orbit was a bizarre anomaly. You had to do all these mathematical gymnastics to even try to explain it. It was a high curvature path. But for general relativity, it was a direct, natural prediction. A low curvature, straight line path. The confirmation wasn't a change in probability, it was a radical drop in the path's curvature, which massively boosted the justification, the rho, for Einstein's theory.
So, what's the big takeaway from all this? It means we need to make a fundamental shift in how we think. Knowledge isn't a destination. It's not just some point on a map you arrive at. Knowledge is the path you take to get there. There's a quote from the source material that just sums this up perfectly. To know is not just to believe, but to have traveled. Your belief is where you're standing right now, but your knowledge, that's the entire journey that brought you there. All the evidence you gathered, all the work you did, and the geometric shape of the path you took.
And that really just leaves us with one final, very personal question. If your knowledge is truly defined by the path you took to get it, what does the shape of your own path look like? Are the beliefs you hold most dear built on straight, efficient, low-curvature paths, or are they the result of a wandering, twisted, high-curvature journey? Because the shape of that path, that's the true measure of how justified you are.